Hello. Okay, so yeah, I've been working on AI debater and yeah, I have to study as well. So apart from the AI debater, I have to study a research paper uh, called TransFace. So we'll study that paper today. Okay, let's go. Uh, it should be somewhere here. Just here. This is the paper. Uh, It's for face recognition. It's a recent paper, I guess. It's from 2023, I guess. I don't, yeah, 2023. So, yeah, this is the paper we have to study now. Let's go. I studied a bit. Okay, so, yeah. We will maybe also try to make notes. Not in the notepad. No, what is this? Whatever, who cares? Oh, yeah, shit. I completely forgot. I only have 20 days left. No props. We will do this from today. Yeah. I did study one paper though. I mean, I have studied more, but I haven't implemented those many papers. But yeah, okay, whatever. Let's see. We will try to finish it. Finish these as much as I can in maybe in 30 days. Sorry, it's DVMS. Okay, not what you think it is. Let's see. Yeah, we are here. Oh, this is not mine. It's my friends. I don't know. It's some experiment of his. So yeah. Okay. Let's see. Let's see. What's the name of the paper? Okay. Let's go. Let me just close the paper. Let's- Should I open it? Oh, let's go. Let's go. Let's go. Hmm. Let's see. I have studied this much, so I'm not gonna study it again for you. Uh, okay. I'm here. Annual patch level data implementation strategy and this course for it based FR background. The main steps of the strategy are: first, we insert a C module at the output of the transformer encoder and utilize the scaling factors generated by S to find about the okay guys. Okay, let us see what okay, that works, right? Uh, Patch level automation. Yes, module. First we insert an SE module. Yes, and the output includes scaling factors. Okay, I don't know what exactly they mean by. We have to see what the scaling factors are. How are they used? Second, we employ a linear mixing mechanism to randomly protect the amplitude information of the dominant bias. Let us see what the amplitude information is about. Let us see. It could be the intensities of the color, right? By applying Fourier transformation to an image, we get its magnitude as well as phase spectrum. I don't know what Fourier transformation is. Yeah, I should, but I don't know. What is amplitude information? What is the amplitude of an image? It is the intensity of different frequencies. Yeah, exactly. That's what I thought. Therefore, it holds the geometrical structure of the feature image, that is the change in uh, spatial domain. Okay, so it's basically the intensity of a color, I guess, right? Yeah, it's something like that. Second, we employ a linear mixture. What's what's the meaning of okay, sure, that's it. Okay, so we store the amplitude information of an image to, you know, yeah, data augmentation. Finally, we feed the recorder structure image X bar into TransFace model for supervised training. Okay, okay. So let's see what that is. Uh, Mathematically, given an image X, we denote a sequence of decomposed image patches as X equals to okay. So let us write that down. So say X equals to Xi would be the patches. Okay. So those are the sequence of patches uh, that would be converted into some encodings, right? And it's an image patch and then there's the total number of patches and the output of the transformer encoder. Let's pass to a transformer to a transformer encoder. So you get so now we have F9. These are the outputs from the transformer, okay? So where F represents the local token, yes. Then all the local tokens extracted by F will pass to the SE module, and S be the module S and be reskilled as importers. Okay, so after this, after passing through the transformer, uh, so we pass it through the transformer, okay. Now after passing through the transformer, we pass this through the uh, SE module. Uh, okay, that's the scaling, I guess, right? So it gives some input outputs K1, K2, K3 for each F1, F2, F3. So it scales them maybe up or down based on how important those are. Okay, that's what it is, right? See, then all the locally extracted by F will pass to the SE module and be rescaled as F1. So yeah, so where K1, K2 denote the scaling generated by F. Actually, these scaling factors of local indirectly reflect the importance of the local. Yeah. So the basically SE module, what it does is uh, gives out a number which could represent the how important the patch is in facial recognition. So yeah, so yeah, that's it. Which scales the encoder output as KI and FI, where oh sorry, shit, where KI could I'm sorry with the spellings, okay, taken as how important the patch is to FI. FI is facial recognition, okay. Hmm. Yeah. Actually, yeah, that's what it is. We further normalize these scaling factors using the softmax function. Okay, according to the top k largest normalized scaling factors, we can screen out the top k dominant patches and the model k is about the top most. Okay, to relieve the VITs from overfitting to these dominant patches, and natural idea is to let the model see more diverse patches. Motivated by the structural importance preserving property of the Fourier phase spectrum. Okay, I don't know what that is. Arbitrary spectrum information of the domain matches using a linear mix mechanism and keep their phase spectrum information unchanged. Okay. I have to see what that is about. Okay, so yeah, we get the top k largest normalized scaling factors to leave the VIDs for all particular. motivated by the structure information preserving property. Okay. So there is a structure. Okay, the main problem in data argumentation and an animal image is the losing of structural properties. So this Fourier phase spectrum transformation, I guess, doesn't have that problem. So we use that to our advantage here, but I don't know what Fourier phase spectrum is about. So yeah, we propose to better the amplitude spectrum information of the dominant patches. We okay. So the point here is uh, amplitude spectrum information could be changed or disturbed uh, without having a problem with preservation of facial structure, I guess. So that's the point here. Okay, I have to see what that is about, but yeah, the point here is the preservance of structural property uh, even though preserving the excuse me. Okay, so yeah, that's my coffee. Okay, yeah, let's see. Mhm. What? Okay, let's see what's Fourier transformation is later. So Yeah. For a single image by the xi, its Fourier transform t of xi can be expressed as. Okay. Let's get better. It's better. Okay. So this is something about Fourier transform. I don't know what Fourier transform is about. So okay, let us just say we have the amplitude spectrum and phase spectrum of the image from Fourier transform. Okay, to effectively construct diverse images without destroying the fidelity and structural information, we employ a mix-up type mechanism to linearly mix the amplitude spectrum of the domain patch xi in random patch. What? I don't get it. You mix up like mechanism to linearly mix the amplitude spectrum of a dominant patch and a random patch. Oh, why? Uniform. Okay. We then combine the mixed amplitude spectrum with the original phase spectrum to reconstruct a new. Whoa. Oh. Oh. Okay. I will write as much as I understand. Okay. Let's go. So. What? Okay. Let's go. So we have F. Fi. Sorry. No. Wait. So we have the K dominant patches from that. Apply. First step. Second, apply Fourier transform on the patches and get the amplitude and phase spectrum units. Spectrum as P into A I plus 1 minus P into random patches whatever the spelling is, bro. Amplitude, right? uh, where P is from u of 0 comma alpha and alpha is a hyperparameter, and the next one is alpha here is a full comma and another. Yeah. So now get the d of x from a bar of x comma p of x, and say f is t dash of x. Now my x dash, sorry, x dash I is t inverse of t dash of x which is used for training. Okay, so that's the point. Uh, One thing I didn't understand is, so you pass it through the transformer and then you get the dominant batches, and then you use those dominant batches, uh, you disturb those dominant batches and then pass it further into the network. But are we passing them again into the transformer or not? Right? That's my question. We feed the image into the model for supervised training. Okay. For we denote the local tokens extracted by F as okay. What? For the argument image, we denote the local tokens extracted by F as, which will be further added into SA module S and rescale. Then all the rescale local tokens are concatenated into a global token, which is used for subsequent effort task wire classification. I don't understand. Okay, let's see. We have initially got an image, right? Uh, One thing I don't understand here is okay. It's like I think it's like you pass the image to your transformer and then you remember the top K patches for this image. What? Okay. I mean, using those you change the image. But for this training set, you just concatenate them and pass them. But in the next epoch, now the image is not the original image but the transformed image, right? That's what you're doing, right? I think so, yeah. Okay. As shown in the reference, hard sample mining technique is often okay. So you get it right. I think I got it. I don't know if I'm right or wrong. So you get the image and you change the image, but in the next epoch, when you pass it again, so now the image is not the original image but the transformed image. So the image keeps changing on its own. Yeah, that I think that's the key thing here. I don't know, not sure. We have to think about it again. But yeah, it definitely works with overfitting, right? Because it's not the same image and the model just can't remember it. Entropy based hard sampling mining strategy. As shown in the reference, hard sample mining technique is often adapted to further boost the model's final performance. Previous works on hard sampling mining, such as are especially designed for CNS. They aim to encourage model to explicitly emphasize the impact of hard samples. Okay, I think hard samples mean that those that are difficult to classify, either as same or either as different. Doesn't matter. Hard sample, I think, is that. I think something like this, right? You can't exactly. I mean, it is difficult to identify them. Identify. I mean, yeah, which class they belong to here. So yeah. However, the recent study has demonstrated that prediction of is mainly determined by only a few, which means that the global token of VIT may be dominated by several local tokens. Therefore, for VITs, it is suboptimal to use such bias indicators to mine hard samples, especially when some dominant local tokens are ignored. To mine hard samples more precisely, motivated by information theory, we propose to measure sample difficulty in terms of total amount of information contained in local tokens. Okay, as demonstrated in figure 4, high quality faces usually contain richer information and thus are easy to be learned by the model. Low quality faces such as the faces and low context faces usually contain relatively less useful information, so they are more difficult to be learned. Right. When we regard a deep neural network M as information processing system, we can abstract its topology in the graph in a graph. A series of neurons from the vertex Z and the connection between neurons found the vertex. Okay, for any Z and Q, EQ denote the values of each vertex C and each edge Q represent respectively. Thus, the continuous state of the neural network M may be defined as this way. The total information maintained in M can be measured as entropy of the set. Okay, E of Z is the okay. You can take the value of a vertex as the bias of the vertex maybe, and the value of the edge as you know the weight of that edge maybe, and the total information in the neural network as entropy of the network. I mean entropy of the set, especially easy measures the feature representation power network M. In our work, we focus on entropy of the latent features rather than entropy of. I don't understand. I really don't understand this. There is something I really don't understand here. Okay, I think we will get back to this later. Okay, let's see the experiments. We separately adopt datasets and recently proposed uh, large scale to for evaluation we employ. Okay, yeah. Our experiments are usually using on PyTorch and Media V100 or as basic class. Okay, we follow to employ ArcFace as the basic classification and as the basic classification laws. We follow to employ ArcFace as the basic classification laws and crop all the input images to by retina face. Okay, to optimize the width based FO model, we apply Adam W optimizer with a weight decaying of 0.1 for better convergence. Okay, the base learning rate is set for S1 MV2 is set to 183 and I mean 10 power 0.00, and for Glent 360K. Okay, the detailed architecture fit models can be found in inside face. Okay, the SC model consists of two fully connected layers with 144 neurons followed by a relevant sigma. Creation function respectively. Note that all the models are learned from scratch without pre-training. In practice, we adopt variance instead of entropy to measure the amount of information contained in each local token to optimize the models more stability to. Okay, instead of entropy we are using variance. Okay, and then the results. TransFace on Gen 360 can compare with other methods and various methods. We can table 1 is this is table 2. Okay, this is table 1. Pretty impressive, right? I mean, it's the top in all of this. I I think S, B, and L represent the size. I mean, like small, big, large. I don't know. And two variants of S only introduces the SE module in this model and based on. Okay. Mm-hmm. Okay. Okay. So only S is less, right? So mixed DPAP and SE both mixed gives us better results. That's what you're trying to say, right? The comparison is almost like equal. But yeah, the results gathered in table 3 uh, reflect the following observations. Compared with VITS, the accuracy of VITS SSC is slightly improved due to additional SC module data, outperform which is better than the amplitude spectrum. Nice, nice. Okay, so I didn't really understand what EHSM is. Didn't really get a good idea of EHSM. Let us read it once again, yeah. Let us look at the image and try. So weightage in the arrow is weightage in the error is given by HSM, right? That's what you're trying to say. So there is a function called I mean, yeah, that, and you use it to weigh the loss. Yeah. Okay. So yeah. Okay, I will tell you what I have understood till now. Okay. Uh, so first the DPAP, where I mean, the C module is like two layered, so where you pass in all the patches, and I don't really understand the SC model how it works as well. Though. How are we scoring that exactly? Mhm. Uh, I don't get the architecture of a C model as well, dude. Uh, they did say something like for the whole. Uh, inside face, huh? What? Oh, something happened. Where is it? Where is it? Where is it? Yeah. So it has 144 neurons fully connected layer. Okay, so Okay. Okay, I kind of understand it. So let us say there is a patch, okay? So my model is dominating looking at one patch, right? So it wants more information from that patch. So when I linearly transform the SE model, so my models, let us say, want to look at a patch. And there's a dominant patch with, let's say, there's a patch of an eye. So my model, when it looks more at the eye, my SE model, like, what does it do? It helps the model improve, right? So it gives more weightage to the patch, the, to the eye patch. So we take that as an advantage, and we disturb it. So yeah, that's what is happening. We know that it is giving more weight to that patch. Uh, so we disturb the patch by looking at the SE model. Uh, that's what is happening. Yeah, I think that's the point here. I thought about it. I think that is what is happening here. Okay. Yeah. Okay. That's it for now, and maybe we will look into it later. Goodbye. Bye bye.